reminding me. I believe that recordings are important. Let's see, we've got it running now. And this is a good place to run it because we're starting to talk about the lecture material. Okay, I pointed at a PDF file to desktop with some physical constants. I've got a bit of reading to look at. These links will reiterate or have already reiterated in homework 1. Many of you have started homework 1. And you'll see other links that I refer to and which will appear in the problem set. Okay. I hope everyone can zoom. Okay. Let's see. Okay, this is Unit 1 of the course. This course, more than thermo courses, is often taught from a historical perspective. So I'm going to talk about quantum mechanics, which you've all heard of. And its origin, or as opposed of, I misspelled mechanics. Versus classical mechanics. Okay, classical mechanics is what you learned about in physics 1 and 2. You know, with problems with the cannonballs and the potential energy and the kinetic energy. And we'll talk about some of the ideas, a lot of the things from classical mechanics and their quantum equivalence semester. Historically, in teaching the course, we begin the conversation not with something from chemistry, but with something from physics, the classical view of light. And here we have a picture of the classical view of light. The classical view of light, by the time that quantum mechanics was discovered, around 1900, is that light, or any kind of electromagnetic radiation, is a wave, or acts like a wave. Specifically, it acts like a wave of oscillating electric fields. The diagram taken from the text shows you how the electric field vector goes waves up and down in time, and an orthogonal magnetic field vector that waves up and down in time. This wave picture of light at the end of the 19th century had won out over the particulate view of light, which is to say we view light as a tiny rock, which had been the viewpoint way back in Newton's day, hundreds of years ago. Okay, I'm looking at the picture on the second slide. This is a picture of the double slit experiment, which convinced scientists light was a wave instead of acting like little tiny rocks or microscopic little blobs that fly through the air. And one of the things waves do that little tiny blobs or rocks do not is engage in diffraction, which you see in this picture and in this picture below at the bottom page. This is a picture of the classic, quote unquote, double slit experiment. The idea is you have a beam of light, as you see here, waves of light, and you aim the beam of light at two slits. See, collimated here, let it pass through this pinhole here at 0. And then the waves of light are aimed at two slits. The magnitude of the slits and the distance between them about on the same order of magnitude as the waves of the light. Then, and the picture illustrates it, but I'll go ahead and draw over it anyway. Well, if it's water, you could imagine ripples coming out one slit and waves of rippling out over slit at the other slit. And where the waves overlap coming out of the two slits, the peaks get very high. And that is seen with radiation. Well, here's a model of the experiment showing the bright bands where waves add together, making a series of bright lines on a photographic plate, for example. Okay, you just need to keep this in mind for later when we talk about other types of waves, but the thing that convinced scientists light was wavy and not blobby was the pattern, the interference pattern that you could obtain in a double slit experiment involving light. Okay, so if light's going to be a wave, we have to know important electromagnetic wave properties. I've zoomed in up to the top of the page here myself. Okay, first, we know, or you've probably heard, that light waves move really fast. The speed of light is 2.9979 times 10 to the 8th meters per second, or 300 million meters per second. Not infinitely fast, but really darn fast. And a wave, light waves included, has two important properties, frequency and wavelength. So I'm going to draw a picture of a wave down here. Okay, this is not the greatest art, but I hope you get the idea. Matter of fact, can I start over? Okay, I guess this will work clear enough. All right, so our wave is traveling this direction. You can tell because of the arrow. Every wave has a thing called a wavelength, lambda. This thing is a lambda, which is the distance between two peaks. There is a thing called the frequency. Frequency is about, if you stand in one spot and watch peaks go by, how many peaks per second? So typical units for frequency are reciprocal seconds, which are called hertz. Now, of course, the units for wavelength, if we use standard units for wavelength, would be meters. Now, the speed of any wave, including light waves, is frequency times wavelength, or C equals nu lambda. Okay, I'm going to clear the board. That way I've got room to write. So typical example problem, for example, is FM radio stations broadcast in megahertz. So one of the local radio stations, for example, broadcasts at 99.5 megahertz. At this point, and there are homework problems like this, you should be able to answer questions like, what is the corresponding broadcast wavelength? Excuse me. And speed is the product of frequency times wavelength, or C is nu times lambda. Oh, I should, by the way, point out the variable we use for frequency is spelled V, but this is Greek, so it's pronounced nu. There are two possible pronunciations of nu there. It's important not to confuse nu and V in this course, or with any of the V's that they're going to be in this course, so I will try to be helpful and keep that clear. At any rate, right now we're talking about C is nu times lambda, so we're solving for lambda. Which naturally is C over nu. And I take the velocity of light, well established by experiments at the beginning of the 20th century, and divide by the frequency. And here I have to use standard units for frequency. So 99 megahertz is 99.5 times 10 to the 6. Or 9.95 times 10 to the 7th reciprocal seconds, or megahertz. I get 3.01 meters. Okay, you can see this kind of information reiterated in the chart I borrowed from LibreText below. Radio waves are quite long, having wavelengths excuse me, wavelengths of a meter or more. And correspondingly, lower frequencies than you will see for example, infrared radiation, which you've all heard of, or visible radiation with wavelengths generally between 400 to 800 nanometers. Questions so far? Okay. So like I say, everything we've talked about so far has been classical physics. Classical physics begins to break down when it tries to model and understand a phenomenon called black body radiation. Okay, some of your links and perhaps some of the things you talked about in some of your physics classes. Discuss black body radiation. Okay, for our purposes, a black body is a mathematical doodad which has been invented by scientists to try to describe the fact that hot objects emit radiation. Okay, anybody who's ever been camping knows that hot objects emit radiation. The coals of your campfire are hot. They give off orange light. Perhaps you've even stuck a poker into a hot fire and heated it till it's orange and seen the orange light that comes off. So you know hot objects emit radiation. For example, things around your body temperature emit IR radiation. And this type of radiation is what night vision or IR goggles detect. If you get a piece of metal hotter, it emits orange radiation. So you see, going back to look at the last slide on the handout, that the hotter an object it gets, the shorter the wavelength of radiation it emits. Now, it doesn't emit at a uniform wavelength. So, for example, an object at 1,000 Kelvin will emit radiation, but the peak value is at a longer wavelength than the kind of radiation emitted by an object at 2,000 Kelvin or an object at 6,000 Kelvin. The higher the temperature, you see, the shorter the wavelength. I always say, the higher the temperature, the shorter the peak wavelength, the peak wavelength being the wavelength at which the most or the most intense radiation is emitted. Okay, the picture is an example of the radiation emitted by the sun, for example. Stars act a lot like perfect black bodies. Most other objects act like imperfect black bodies. So you see that the distribution of solar radiation closely follows and peaks at a temperature corresponding to an object with a temperature of about 6,000 Kelvin. Okay, this empiric relation can be summed up empirically with Wien's law, in which the peak wavelength of radiation can be related to the temperature by this inverse proportionality constant. So again, as we see from this equation, which you will use for a homework problem, shows the inverse relationship between temperature and peak wavelength. Okay, you can try to model this with the ideas about extant about physics, which is to say the classical model of radiation, at about the beginning of the 20th century or the end of the 19th century. Okay, they call this function of the wavelength, which maps the intensity rho. Okay, so this blue thing I drew up here is rho corresponding to around 6,000 Kelvin. Classical physics developed a theory that said, well, rho should look like this, which is to say, if I come over here and plot the wavelength versus rho, they predict something like this. T is a constant in the numerator, or well, it appears in the numerator. The fourth power of wavelength appears in the denominator. At any temperature, this describes a hyperbola like what I've drawn to the right. Okay. Problem with this picture is clearly it does not look like the picture up above, which shows a peak value for the wavelength, and then it falls off on either side of the peak and tip. Okay, so basically the story is classical physics tried to model the behavior of hot objects and pulled a big dud. Okay, coming to the top of the next page. The problem with this was fixed by a scientist known as Max Planck, who I'm sure you've at least heard his last name. Planck fixed the problem by assuming that the permitted radiant energy coming from the hot object is given in such a way that the energy that is released is a multiple of the frequency. And in fact, the allowed values of n in this equation up here I'm drawing on are 0, 1, 2, 3, 4, 5, 6, 7. H or Planck's constant was a fudge factor to make it come out right. Okay, so here is the rho function that Planck comes up with by supposing that the energy comes out in packets proportional to the frequency. Okay, this formula, actually, I'll leave there. This formula, which I've drawn a circle around, actually works. In other words, if you plot rho, you get the curves that are observed in real life. Okay, so you don't need to, we're not going to plug in anything to this function or otherwise fool around with it. I just want to observe that the black body theory was fixed. And in the process, Planck had to invent a fudge constant, which worked out to 6.62608 times 10 to the negative 34. The units of the constant are joules times second. Okay, you see that the constant again appears in this formula here. But again, we're not going to do any kind of problem solving with this formula. Okay, this came in helpful of explaining another thing called photoelectric effect. Okay, unlike the thing with the perfect black body, this is somewhat easier to understand. Conceptually, what happens in the photoelectric effect is you have a sheet of metal. Now, in the experiments on the photoelectric effect in the 1900s, what happens is you aim a ray of light at the metal. So I'm going to draw a ray of light. You can tell it's a ray of light because it's wavy. And you can tell it's moving toward the sheet of metal because of the arrow. Okay, now naturally, this ray of light has some frequency. Okay, you aim a ray of light at a sheet of some metal, and an electron pops off. We know no electrons are tiny little rocks. So here is an electron coming off the metal. Okay, the photoelectric effect is actually what makes the door open at Kroger. or in principle, any electric I beam works by the photoelectric effect. If you break the electric I beam, which is to say the radiation or ray, then electrons stop coming off a sheet of metal, and that stops a current, an electric current, which the ray is generating. And that cessation of current is a switch which tells the door to open. So this technology is pretty commonly applied. Experiments on its property didn't take place till 1900. And the first thing is observed is that no electrons come off unless the frequency of the radiation, which I've drawn in the picture, is greater than some threshold frequency nu naught. Now it's important to understand that nu naught, the threshold frequency, is a property of the metal. In other words, there's a different one for each metal, a different threshold frequency for each metal, and the frequency of the radiation that you aim at the metal has to be greater than the threshold frequency for electrons to come off. Third, the kinetic energy of the electron increases as the frequency of the radiation, not the intensity of radiation, increases. In other words, it doesn't matter how bright you make the light, which is what intensity is about. But if you increase the frequency, the electron goes faster. What intensity does is increase the number of electrons ejected. In other words, if you want more electrons, make the light brighter. Okay. The theory which explained the photoelectric effect was forwarded by Einstein about 5 years later, and this is actually the thing they gave him the Nobel Prize for. And the essence of the theory is, and this is Einstein's quote-unquote quantum theory, is to give up on the idea of the light as a wave, at least partly. Instead, we go ahead and think about light as a bunch of tiny little rocks called photons. Now, the energy of the photon is equal to Planck's constant times the frequency of radiation. Okay, how can something with a frequency, how can a little rock have a frequency? Well, we'll ignore that right now. Okay, the light has a frequency and it comes in little rocks, and you will multiply h by the frequency to get the energy of the photon. Likewise, each metal has a work function. Now, the work function of the metal is energy required to remove an electron. From the sheet of metal. Okay, the work function is different from the ionization energy of an atom. But energy required to remove an electron from the sheet of metal is the work function, W. And that is, of course, related to the threshold frequency by Planck's constant. So the formula about the work function and the threshold frequency is really the same formula as the photon energy formula. If the photon has the threshold energy, it has energy equal to the energy to remove the electron. And then naturally, or by conservation of energy, the kinetic energy of the electron is equal to the energy of the photon, which is h nu, minus the work function. Okay, there are links about this, and there are problems about this. There are formulas about this. In some form of the formulas, the work function is W, and other it appears as a Greek symbol. My advice is understand what's going on in the problem and don't worry so much about the formulas. Okay, let's zoom in up to the top of this. Figure 6 of the book shows that electrons start to appear at the threshold frequency of radiation. If you shoot a sheet of metal with radiation equal to the threshold frequency, the electrons have no kinetic energy, which is what appears on the left. But the electrons have more and more kinetic energy as the frequency increases beyond the threshold frequency. Okay, I recommend, well, in addition to attending to this lecture and the example problem I'm about to do, there is an additional example problem at this link. Okay. If we zoom into the top of this page of the lecture handout, we have an example problem involving the photoelectric effect. We're going to calculate the speed of electrons ejected by light of wavelength 500 or 200 nanometers. Okay, there are a couple of constants there. Okay, let's begin by thinking about the case of the 200 nanometer incident radiation. Okay. And we're finding the speed of electrons ejected from a sheet of cesium. Okay. Tables often present work functions in terms of energies of electron volts, which you may have actually seen in physics. An electron volt is 1.6 times 10 to the negative 19 joules. It's the energy of one electron accelerated through a potential of 1 volt. It's not a lot of energy. So we need standard units to deal with this, just like in PChem 1. First thing to do is convert the electron volts to the joules. Using the value of 1.602 times 10 to the negative 19th. And I get 3.428 times 10 to the negative 19 joules. Feel free to follow along and check me. Okay, now remember that this thing is the work function. We could try to find the energy of the photon. we're given 200 nanometers for the incident radiation. 200 nanometers, remember, is 200 times 10 to the negative 9 meters. Or 2 times 10 to the negative 7 meters. Okay, so we can find the frequency, or what's new, by dividing c by lambda. All right, now c is always a constant in base units of meters per second. It's good to convert a wavelength to meters. For the wavelength. And we obtain a frequency. Of around 1.5 times 10 to the 15th, of course. And that's 1.50 times 10 to the 15th reciprocal seconds or hertz. All right, this is a very typical calculation of this course. Given a frequency, you should be able to determine a wavelength. Given a wavelength, you should be able to tell me what's new. And that's about the quality of the jokes around here, too. Okay, this number is 15, not 16. Okay, so I'm going to summarize here in the chat box. All right, it's the difficult thing in a photoelectric effect problem. Well, one of the things is keep track of what one number applies to what thing. So I have a work function in joules, which applies to the metal, and I have a frequency of the radiation, which applies to the ray of light you're aiming at the metal in hertz. I'm going to clear the board now, if there are no questions. Okay. Okay, so clear on the board. All right, the energy of the photon is h nu. And really, the only reason I solved for the frequency was so that I could use it to solve for the energy. Okay, so again, keeping track of what we're calculating when we're using the formulas. This thing is a photon energy, and it's h nu. So take h multiplied by a frequency, get a photon energy. I get 9.94 times 10 to the negative 19 joules. Okay. So this particle of light, or radiant energy, you're supposed to imagine, the photon, is actually not a whole lot of energy. It's a very tiny amount of energy, 9.94 times 10 to the negative 19. Okay, important fact is, I'll put it in the chat box again. (9.94 times 10 to the negative 9 joules), which is greater than 3.428 times 10 to the negative 19 joules. The energy of the photon, h nu, is greater than W, so the effect can take place. The energy of the photon, or rather the energy of the electron, is the energy you put in minus the energy to get the electron off, or (6.51 times 10 to the negative 19 joules). Questions so far? Okay. Now, an electron has a mass of 9.10939 times 10 to the negative 31 kilograms. Actually, the kinetic energy is negative 1/2 mv squared, where v is the speed of the electron. Okay, it's very important not to confuse, well, in these problems, and again throughout the course, to avoid confusing the v with the nu. Speed of electron actually is a b. All right, so you can solve for v. It's 6.51 times 10 to the negative 19 joules. Oh, times 2. Divided by the mass. In kilograms. And we have seen back in PChem 1 that if you take the base SI unit of joules, divide by the SI unit of kilogram, take the square root of the result, you obtain the answer in meters per second. This should be a 5. And I get 8.45 times 10 to the power 5 meters per second. Okay, questions on this problem? Okay, keep your eye on the numbers in the chat box. You should be able to tell me what is the threshold frequency of cesium? Divide the work function by Planck's constant. That's correct. Now, in order to have that make sense, of course, you have to put that in joules. But again, if you put Planck's constant and its base units, and divide by the work function, which was actually 3.428 times 10 to the negative 19 joules, you get a frequency out. I get 5.17 times 10 to the 14th. Okay, so we can calculate a frequency quickly enough. Let me try a more qualitative question. Let's think about the other half of the problem. will radiation of wavelength 500 nanometers cause the effect in cesium? How do we answer? Brian says determine if the energy is greater than the work function. Okay, we could do that. Now, I'll go ahead and I'll show you a trick that will come in handy throughout the rest of the semester. We know the energy of the photon is h nu. We also know that nu is c over lambda. Paul says find if the frequency is greater than the threshold frequency. Yes, that would also work. If we don't want to stop to calculate the frequency, we can calculate the energy as hc over lambda by substituting c over lambda here in for nu. So yes, we could calculate the work function. Yes, we could calculate the threshold frequency, which might even be easier. So let's do that here real quick. I can take HC, I can divide by lambda, which by now you will all recognize as 5 times 10 to the negative 7 meters. And I get an energy of oops, hit the wrong button. I basically get 4 times 10 to the negative 19. 3.98 actually. Oh, okay, so I've calculated this number. This is greater than W. So the answer would be yes. The effect would be created. Likewise, as Paul says, I could calculate the threshold frequency. I could calculate the frequency and compare it to the threshold frequency. And I should also get a yes. Finally, allow me to define the cutoff wavelength, which is the wavelength corresponding to the threshold frequency. So W naught is C over nu naught. Or 0.9979 times 10 to the 8th meters per second over 5.17 times 10 to the 14th. I get 5.79 times 10 to the negative 7 meters, or 579 nanometers for the cutoff wavelength. Okay, notice that the cutoff wavelength is 579 nanometers, but we have seen that 200 nanometer and 500 nanometer radiations both cause the effect. Because of the inverse nature of relation of wavelength and energy, the eighth length of the incident radiation must be less than the cutoff wavelength to observe the effect. All right, are there questions at this point? Okay. Okay, as you'll see on the next page, I've got some stuff about hydrogen atoms. I guess I'm going to stop here today. And we will pick up this discussion on Thursday at 9:55. Okay, are there questions at this point? Okay. I can turn that off. I'm going to go ahead and stop the recording.